Hello and welcome to the second session of our workshop series Introduction to Engineering Simulation, delivered to you by SimScale, Simulation in your web browser. My name is Milat and I will be your host today for our session. And first of all, I would like to make sure that everybody can hear me loud and clearly. And you might notice we're using a software called GoToWebinar to deliver the live stream of the webinar on your desktop. And right now, you should see the so-called GoToWebinar control panel on your computer or your tablet or your phone. And there's a button called Raise Your Hand. And in the case you can hear me loud and clearly, please click on the Raise Your Hand button to show me that everything is working fine. All right, I see the first couple of hands and it seems like everything is working smoothly. Perfect. In the case you have problems with the audio quality, for example, we also offer a toll-free alternative, our audio service numbers. And right now you can see different numbers on the screen for different countries. And please, in the case you want to listen to the audio of the session using your phone, just dial one of the numbers and enter once you're asked the following access code you can see on the slide. Perfect. All right. And since everything is working from a technical perspective, let's start with our journey through the world of thermal simulation. And yes, so let's take a look at our today's agenda. And I think some of you already joined yesterday for our first session. And as you know, this is a workshop series by SimScale, and the aim is to enable and train engineers to get started with engineering simulation on their own. And we have 3 sessions, and every session is focusing on a different aspect or different discipline of engineering simulation. So yesterday we talked about computational fluid dynamics and fluid flow simulations, and today we'll talk about thermal simulation, and tomorrow about structural simulation. However, thermal simulations, that's our topic. And first of all, we are going to talk about the very brief fundamentals of thermal simulation. So what is simulation in general? What does thermal simulation mean? What are the advantages and disadvantages? And how can I use it for product development? And then we will quickly, just for 5 minutes, talk about SimScale, so what we are doing here. And we will introduce you to our free and cloud-based simulation platform. And after that, I have prepared a very nice live demo where we will put you into the seat of a thermal engineer, and together we will set up a simulation and analyze the results. And finally, there is a lot of time for our Q&A. In the case you have a question, please just write it into our question toolbox, which is also part of the GoToWebinar control panel. And we will collect all your questions and I will answer them later during the Q&A. All right, so let's start with the fundamentals. And again, in theory, I could talk for hours or days or even weeks about fundamentals of simulation or thermal simulation. And there are even books or whole university courses just focusing on that. So we will try to make this as short as possible, this part. And you know, our aim in the end is to enable you to use and apply engineering simulation. And therefore we will put a very big focus on the hands-on practical part. However, I still think that it's very important for every engineer to at least to have a rough picture about the fundamentals and really the concept of thermal simulation, and therefore let's try to understand it. First of all, what is thermal simulation? And in short, as indicated by the word simulation, thermal simulations can be assumed as something like virtual experiments on a computer which you use to predict changes in a temperature field inside a solid or fluid body. And this is a very, let's say, abstract and theoretical definition. So let's try to shed some light on this. And basically, thermal simulation is used for different kind of simulations. And we have basically three kind of simulations which are summarized under the term thermal simulation. And what they have all in common is that they are dealing with temperature fields, as I mentioned, and that we are looking in the end or that we're looking in the end for a temperature field, temperature and heat fluxes inside this body or the fluid domain. And yes, we have basically three kinds. So the very first type of thermal simulation is called solid heat transfer simulation, and it's basically focusing on the physical principle of conduction, which you all know. So conduction is heat transfer inside solid bodies. And with this kind of simulation, you can basically predict and analyze temperature changes and temperature distribution in solid bodies for different kind of loads. Like in this example here, you can see a custom designed heat sink for a high performance electronic unit. And this simulation, for example, is representing the local temperature inside this heatsink. And as you can see, we have a very high temperature indicated by this red color here at the bottom of the part where it's connected to the actual electronic. And then the temperature is decreasing, and we have this kind of heat or temperature profile inside this heatsink. And if you take a look, it's obviously that some parts of especially here on the left and the right upper corner of the heatsink could be optimized. And another simulation type, which is summarized under thermal simulation, is dealing with convection. And this one is very familiar with CFD, with computational fluid dynamics. And it's basically CFD simulation, a fluid flow simulation, which is also considering the energy of the flow and convective effects. And for example, here in the example, you can see how a heating system is used inside a room. And the color here is representing actually the temperature of the air. And you can see how the hot air is entering the room at the floor, and how this hot jet is then spreading up and the air becomes cooler. And there's even a third kind of simulation, which we call conjugated heat transfer. And basically, conjugated heat transfer combines the best of both worlds. And all the CHT simulations are basically a coupled simulation we are coupling in detail a solid heat transfer simulation with a convective heat transfer simulation. And a good example is this simulation you can see on the right side, which is representing the temperature distribution inside the case of electronic device. And here we are simulating both the solid heat transfer inside the heat sink from and the heat transfer from the heat sink, from the solid body to the fluid around it, to the air in the housing, and also the convectional effects inside the housing. And a lot of people ask me when I start to talk with them about simulation, well, what is the right simulation type for my problem? And shouldn't I go for, and isn't basically every problem a CHT general problem in general? And that's basically a valid point. In the end of the day, every phenomena or every heat transfer phenomena is including both types of heat transfer, as a conductive part and a convective part. And the job of engineers in the end of the day to decide which of these effects can be neglected and which is so important that we really have to consider it. And a lot of times when people want to do a CHD simulation, for example, to analyze the temperature distribution in the housing of an electronic part and to make sure it won't fail, they initially want to go with CHT, but for most of cases this is not necessary. And a lot of questions can also be answered with a convective or conduction simulation only. And the difference is that conduction simulations, considering conduction or convection, are much easier in terms of setup and stability than CHD simulation, which are coupled and therefore much complex. And therefore my suggestion, whenever you start to think about how you can use simulation for your own project, and especially if you think about thermal simulation, first of all, try to find out what can be neglected, and if you're lucky, your problem will simplify a lot and you will end up in a simple convective heat transfer simulation instead a complex conjugated heat transfer simulation. Right. So another thing I would like to talk about is simulation in general. And since there are different methods used for thermal simulation based on the exact physical principle you want to model, I would like to talk about simulation more in general. So what we call engineering simulation can also be called numerical simulation or numerical engineering. And as the words numerical indicates, it's a little bit different to what we call analytical models. And now let's try to understand what a numerical simulation is by talking first about analytical models. And you may never heard the word before, analytical model or analytic model, but I'm quite sure you've used it on your own for many times. And the basic definition of analytic model is that there is a closed mathematical solution for the entire domain of the model. And in the real world, it means we can only use it for very simplified problems in model, since for most of physical principles like heat transfer or fluid momentum transfer, we have equations which are describing these effects, but we cannot solve them. And therefore, these analytic models, which are very precise, can only be applied on very simple examples. And in school, most of the time, you use very simple analytic model to describe basic physical phenomena. The easiest example is a linear force on a spring. Just imagine you have a spring, and you can remember this kind of experiment at schools, and then you apply a load on one end of the spring, and you try to measure like the elongation of the spring, and then you plot it. You plot the force against this elongation, and what you will find out that there is a linear relationship, and this linear coefficient we call it C, which is the stiffness of a spring. And that's basically a very simple zero-dimensional or one-dimensional model for a spring. And in contrast to that, numerical models are used everywhere where I cannot use analytic model. And usually what you do is that you look for approximate solution of the analytic model, and instead of considering or calculating a solution for the entire domain, we are just focusing on approximation on defined support point and between them. And what does it mean? Just imagine, if we take a look back on the left side and we take a look at this equation, force is equal to stiffness multiplied with length. One thing which we can directly see is that this is an actual mathematical function, which means I can calculate every solution inside my domain, and I can basically I have an unlimited number of points describing this graph. And when I use a numerical model, I just calculate solution for defined support points, like you can see here. And in between them, I just interpolate. And this allows us to simulate very complex issues, because we can reassemble complex problems from small sub-problems which we can solve. And this helps us in the end of the day to analyze and to predict the physical behavior of very complex real-world problems. And Just an example for CFD, and this is something we talked last week about, so if you're more interested in that, you should take a look at the recording from yesterday. And in CFD, it's the same. We have an equation which is describing the momentum, mass, and energy conservation in a fluid. But we can't solve this equation for complex problems and cases like the flow around a wing structure. So instead, we are dividing our wing structure not of small shapes as elements, and then we can look for a numerical solution for this simplified shapes. And then instead of calculating or computing a function for the values of pressure and velocity around the wing, we just calculate approximate values for every center of these cells. Great. So we talked now a lot about the theory of simulation, what simulation is basically about. And I know that some of you maybe want to learn even more about the theory and the fundamentals. And don't worry, we have a lot of free resources on simscale.com where you can get introduced more to these fundamentals, including whole workshop and free online courses about the theory of simulation. We have a simulation wiki and a lot of step-by-step tutorials and documentation. So now let's try to understand how I can use simulation and which potential benefits simulation can add to your product development process. And to understand this, let's take a look on how engineers are designing products and how they were designing products in the past and how they will design products in the future. So generally speaking, independent from the industry, the old and let's say traditional way of designing, developing, manufacturing, and shipping a technical product is that you at some point start with your design project, and usually at a very early stage, after you maybe made some assumptions and some preliminary calculations, you start to design your CAD model. And once you have designed your full model and you have a physical prototype, you manufacture it, then you test it on physical test rigs, and then you try to improve it by changing the design based on the insights of your physical test results. And this loop, optimization loop, is taking a lot of time and is quite expensive because, first of all, it's happening quite late once the whole prototype is designed. Another big problem is that it takes a lot of time because for every design change you need to redesign, remanufacture, and retest your design. And in the end of the day, it's also very limited. You're very depending on your, let's say, data acquisition, and you can only analyze and understand those quantities which you have measured during your test. And compared to this, simulation allows you to design your products cheaper and faster by using the advantage of the virtual experiment we can perform. And a very good example is one of our customers I mentioned already yesterday. It was one of our first customers, and it's a medium-sized valve design manufacturing company. And those guys are designing custom valves for larger industrial projects. And usually when they start to design a new valve, they really had to design the whole valve, define everything, the electronics, the sealing of the housing. And once this was finished, they manufactured one valve, tested this on a physical test rig, and measured the pressure drop of the valve. And in the case they were not satisfied, they had to do all the steps, manufacture again a full valve, and this took a lot of time. And now they're using simulation, and today when they want to design a valve, at the very beginning of the project, they just virtually investigate 3-4 concepts for the valve body, and once they found out using a simulation what's the right direction to develop, they test and innovate most of their design virtually, and just at the very final stage they only create one prototype, do a final test, and then usually they can directly and start to manufacture and to ship it. And if you think about this user story, you might ask yourself, well, sounds like simulation is a big deal and can really help. So why I never heard of it before, or why are only just a few number of companies using it so far? And to answer this question, let's take a look at the graph on the left side. I don't want to talk too much about that graph, but basically that graph is representing which fraction of engineers in the industry are using a technology. And you can see the orange and the green line representing 2D and 3D CAD, as well a blue line representing the adoption of 3D engineering simulation. And as you can see, sorry, especially compared to CAD, the industry adoption is quite very, very low for simulation. And there are basically three reasons. One reason is, this is what we call access barrier. In contrast to CAD tools, which are industry standard for more than 2 years, simulation needs a lot of special infrastructure. You need at least a very powerful hardware, and for most of cases you even need a kind of computing cluster which provides you with the necessary computing power. You need the software licenses, and usually you have to install the software on the cluster, which is not very easy. You have to install local clients, configure everything, and assign licenses. And this is a lot of work, and especially for small companies who just want to use this technology. It does not make sense to hire a HPC administrator first and someone who can care for the processes. Another problem, which is very much associated with the access barrier, is what we call the budget barrier. All the traditional simulation tools were designed to be used by very big companies, and they come with very traditional old license models, including very high fixed expenses for software, and we're talking about annual expenses. So if you want to start with simulation, you usually have to spend 10, 20, 30,000 euros in upfront just for buying the hardware and software licenses for 1 year. And this is quite expensive, and for a lot of small companies, therefore, it's just not possible right now. And the final reason, which is maybe one of the most important reasons, is what we call the know-how barrier. Even if traditional simulation tools would be available and accessible for all engineers, all these tools have in common that they were designed to be used by simulation specialists, simulation engineers, and numerical experts. And in the end of the day, you want that your designer and your design engineers can use these tools, and therefore there is right now a big lack of tools which can be used by let's say every engineer. And that was the reason why SimScale was founded more than 5 years ago. SimScale is a spin-off from the Technical University of Munich, and back then we were frustrated by the low adoption of simulation in the broad industry, and we saw, well, it's such a great technology which is used for making airplanes more safe, for making race cars faster, and why isn't it available to everyone? And when we started to think about the reasons, we had an idea of making simulation accessible to everyone. So the vision of our company is democratizing engineering simulation. And therefore we have developed the very first cloud-based simulation platform, SimScale. And SimScale is a 3D interactive simulation platform which runs on your web browser, and it gives you access to unlimited simulation capabilities by just using a standard web browser and internet connection. You don't need to buy any dedicated hardware, to install any software, or to download or buy any software, and everything you need, including the computing power, storage, and software, is delivered to you through your web browser. And together with the accessibility, we also made a case for the costs. And SimScale comes with a very unique freemium price model, which means you can basically access and use all simulation features of SimScale for free. And we have a so-called community plan, which gives these features to everyone who is interested. You can just register for free and start to simulate. And since I told you that know-how is a big problem, we combined this freemium model with our with collaboration functionalities and community, which means every simulation project created by a free user is public to other users, and other users can use this simulation project as a template to get started with their own design. And this is part of our vision of creating a simulation ecosystem where everybody can get started in just a couple of hours with simulation. And for those of you who don't want to share or who are not able to share, let's say, the simulations, we also offer professional plans which guarantee 100% privacy. And before we start to take a look at our live demo, let me just tell you about the capabilities of SimScale. So SimScale basically covers all three major disciplines of engineering simulation, including solid mechanics, fluid dynamics, and thermal simulation or thermodynamics. And we also have special solvers for niche phenomena like particles. And with our solid mechanics capabilities, we can basically simulate everything which is happening inside a solid body as a result of external loads. And these loads can be forces as well as temperatures. With our CFD model, as I mentioned, if you're interested in that, you should take a look at the recording of yesterday's webinar. You can simulate everything related to fluid flows. And with our thermal simulations, you can, as I mentioned, simulate everything where heat transfer is involved. Great, so let's now take a look at our live demo. And as I mentioned already several times, our aim is really to get you started with simulation. And therefore, we will now want to focus on some more hands-on parts. And just because some people wrote it already in the chat as a question, we have not sent out so far the link to yesterday's webinar, and right now we are cutting and rendering the recording, and we will send it to you latest today around noon. All right, so now let's try to understand what engineering simulation means and what kind of benefit it adds to our product development process. And therefore, let's now put ourselves into a seat of an HVAC engineer. And just imagine you're working at a company which is designing, building IT rooms. And for example, if you want to run simulation on your own, sometimes you need this kind of IT rooms because you need so many servers to run the calculations. And when you think about such big IT rooms, you should keep in mind that cooling is essential. And in the most of the cases, I have around 10 servers in such a rack. And if just every server is just consuming around 1 kilowatt of power, I have in total like up to 100 of kilowatts of energy. And all this electrical energy is transferred into heat. And I need to somehow to remove the heat from this IT room to make sure my components and my computers will not overheat or get damaged. And usually when it came to design such rooms, there were several standard concepts which people used all the time. But especially today where energy costs are rising, energy efficiency is the key. And especially here, simulation can help to improve the energy efficiency of this IT room by improving the convective cooling of the racks. And so our aim now is to first of all run a simulation to predict the surface temperature on the racks, and based on that to develop a design alternative which is better in terms of performance at the same level of energy consumption. And this is, yes, our server room. As I mentioned, you can see here we have the server racks. and the cool air is supplied through an opening here at this wall, and we have an outlet duct here where the hot air is removed from the room. And now we need to set up the simulation. And we have basically 3 steps for every simulation, independent if it's a fluid flow simulation or a thermal simulation. And the first step is called pre-processing. And this step is about, as the name say, preparing your design, your CAD data for the simulation. And there are 2 major parts of pre-processing. The first part is about cleaning and preparing your actual CAD model, which means you need to make sure your model is watertight. You should take care for cleaning up the model as much as possible. This means remove very small surfaces or intersections and really make sure the model is clean from a CAD perspective. And once this is done, you need to mesh the model, which means that, and we'll just show you how you can do this, you are going to divide the domain of this IT server room into a lot of small hexaeders or small elements, and doing that, or by doing that, you are defining the local accuracy and the local resolution of your simulation, because you should remember, in the end of the day, the simulation tool is only calculating one value for pressure and one global value for temperature and flow velocity for each cell only. Alright, and once we have meshed our geometry, we can set up the actual simulation, which means we will define inlets and outlets and heat sources inside the room. And finally, we do so-called post-processing, which is about analyzing the 3-dimensional simulation results. And now let's switch to the web browser. And as I mentioned, you can register free on SimScale. Just go on simscale.com. And just click on sign up, fill out this form, click on create free account, and you will receive further instruction. In a couple of minutes you've created your own account. And once you have your own account, you can log in, and then you can switch to the dashboard. And from here you can create new simulation projects and access your own simulation project whenever you want. And I also talked with you about the public projects. And now let's take a look at the related simulation project, which is a public project already. And let's say you're starting from scratch and you want to do a server room simulation. You just search for server room, for example, in the public projects, and then you see all projects related to server rooms, and then we can just click here. And since this is a private project, we can copy it to our own workspace, or even just take a look at it first of all. Well, I will now import the simulation to my own workspace. This can take several seconds, and then we will go through this project and I will show you the necessary steps to set up the simulation, and after that we will take a look at the results and try to understand their meaning. Now we can switch to the dashboard. Sorry. Now let's take a look at it. Well, so this is a project. And first of all, one great thing about SimScale is that it supports a lot of different options for uploading a geometry, including exchange format like step files, IGES files, or STL CAD files, and also native CAD formats like Autodesk, SolidWorks, and Rhino. And when you want to create a new mesh, you basically have a lot of options. And you just click on create a new mesh, and then you can choose between several operations. So we have different meshing options, and then you basically just choose the option meshing algorithm you want to use, and then you just need to define the resolution of your simulation. And here we defined like a feature refinement. So we defined a refinement for all the edges of our model. We defined a refinement for the surfaces of our model, and we added some ultra thin elements in the near of walls to properly model the heat transfer and everything which is happening in the boundary layer. And once you have created your mesh, you can directly switch to the so-called simulation designer, and there you can easily create a new simulation. And now let me try to copy the project so that we can make some changes. And it can be done in parallel. And basically you just need to define what is the material you want to investigate. In our case it's airflow. And you just need to define the temperature at your inlet and the mass flow rate, the temperature, the pressure at the outlet. Then we defined a adiabatic boundary condition, which means that there is no heat transfer through these walls. And we defined a heat source for the server racks and a temperature for the walls of the room, and that's it. And then you just need to start your simulation. And now we are taking advantage of the computation power of 32 cores. And this simulation took around 4 hours. And here you can see like the so-called residual. So this is how the simulation became more accurate and accurate with every simulation step. And you can see why the accuracy at the beginning was at 93%. At the end, it's much better. And once we have done this, we can start to analyze the results of our simulation. In the meantime, let's check if I think we have some question which I would like to answer. No. Okay, so 2 questions by Charles. The first question, Charles wants to know if SimScale is developed around the metric system and if all entries must be entered in metric units. Charles, that is not the full truth. SimScale was initially developed around the metric system, but for sure we are also supporting other systems. And especially for the units, we also support American units. So I can show it to you. If you go on simscale.com and on the dashboard, and I click on New Project, I can choose my default unit system. I can use English units or European units. And there was a next question by Charles. He wants to know if SimScale can be used for integrated simulations between mechanical and electronic systems involving transfer functions and block diagrams. This is not supported at the moment, Charles, but from our point of view and our experience with the existing customers and users, usually it's not a big deal to manually map the simulations. And most of our customers are doing, that they're like using this block diagram and transfer function to calculate some kind of boundary conditions which they can use for the simulation to understand what is happening in detail. Right, so now you can see the simulation result. And this simulation, by the way, we can now take a deeper look. Just need to wait until it's loaded. Now, just wait to load the next time step. We can, for example, investigate the velocity or the temperature and the pressure of the air for every and each point inside this control domain. And so I just prepared some of these images. And here you can see the initial design of our server room. And the picture, so the color right now representing the surface temperature on the server racks. And you can see that we have a lot of hot spots, especially on the side, which is more away from the cool air. And especially here you can see like we have these very hot areas, and all in all it does not look very equally distributed. And as you know, when designing such a cooling system, I'm interested in the end at the max temperature. So whenever just at one rack the temperature is too high, I need to increase the cool rate as long as everywhere the temperature is below this critical temperature. And therefore this ununiform distribution of heat is really a problem, and this design is not optimal. And it also becomes obvious if we take a look at the velocity and temperature profiles parallel to the ducts. And here you can really see what is happening. So the on the right side, the cold air is entering here the room, and then it's mixed up with all the surrounding air. And here you can see like here we get these mid-temperature zones. If you take a look at the velocity, you can also see that the reason, or one reason why we have this very high temperatures here is maybe the fact that we have flow separations here. Or if you take a look here, this server here, this one, is really hot. And the reason is that the layout of this outlet is blocking the whole flow here, and we get the fluid flow separation recirculations here, which are not good. Because in the end of the day, you only want to cool the servers, not the entire room. And so this is our initial design. And if we think about it, we want to have more control over the cold air jet. And therefore, let's test a version where we have a lot of small inlets and a lifted floor instead of this big inlet duct. And here you can see the difference. So we have this small inlets in front of the racks. Well, and now I just needed to copy the simulation, copy the settings, and now we can just compare both designs. And yeah, here you can see initial and new design, and this gray surfaces are representing isocontours of temperature, showing how the cold jet is flowing around the racks. And you can see that on the initial design, a lot of this, let's say, cold air jet is lost. While the new design, we have a much better distribution of the cold air around the racks. Especially if you take a look at the local temperature, it's much lower in average with the new design. Here again, a comparison of the initial and the new design. And here you can really see like how this new position is optimizing the heat transfer and reducing the surface temperature on the racks, because this cold airstream is really leaving exactly in front of the rack. And in total, I mean, we still use the same amount of cold air. In total, for sure, the difference is not very big, but if we focus on what we want to achieve, and that is reducing the temperature on the surface of the racks. We are using the energy much smarter right now. And that's really the great thing about simulation. It not only tells us what is happening, but also why is it happening. All right, and now to put it in a nutshell, just by one of this design's iteration using the simulation, we were able to decrease the average rack temperature by more than 10% with just one design change. And I think this is really a good example which clearly shows how easily you can improve existing designs using simulation. I would like also to talk with you about another aspect of simulation. A lot of people ask us all the time, so what's about the accuracy of simulation? And that's basically a very good question. And generally speaking, the accuracy of a simulation depends highly on the input. And therefore, simulation in theory is very precise, but you need to know what you are doing. And this example is a project we used as a benchmark. And the good thing is that we had all the physical data, so we could compare the results we've calculated with our SimScale simulation platform to the physical test results. And red is representing the actual physical results, and blue the results of our simulation. And in both cases, we are showing here temperature profiles, which were measured undefined points. And here you can see that that we have a very good qualitative representation of the values. And sometimes people have wrong expectations. Simulation is not so good in predicting absolute numbers, but it's very good in predicting relative change and therefore to optimize something. And now let's wrap it up. So all in all, what have we achieved? To run the simulation, it takes you around 2 hours of manual time, which includes preparing your CAD model, uploading, preparing all the settings, start the simulations. Meshing, 2 meshes and 2 simulations run for around 7 hours on our platform, and in total we needed 400 hours or 400 core hours to run all the simulation and the meshes. And depending on your plan, the simulation is completely for free, or if you want to use a professional plan, we're talking about several €100 for the whole simulation. And in return, we were able to significantly reduce the facility surface temperature, and it can also help to get design confidence and to understand the new design before we commit on using it. And now we have time for the remaining questions. And first of all, I would like to thank everybody who joined for today's session. And just to make sure you know it, tomorrow, hopefully tomorrow around lunchtime, I will send you an email containing the recording of this session and some useful links to resources related to this online workshop. And first of all, you can watch the recording again and again, but we will also provide you with a link to the actual project and with a link to a quiz. And by submitting this quiz within 2 weeks, you can qualify for a free certificate of participation. And now we have some questions which I would like to answer. And so let's start. First of all, Brandon wants to know if the server racks are at fixed temperature or if it's a transient simulation. The simulation I showed you is or was performed as a transient simulation for the animation, but you can also do for sure a steady state simulation instead if you want to average everything. Godwin wants to know if I'm going to show you solid mechanic analysis in this webinar, and this is something we're going to talk about, but tomorrow there we have a webinar dedicated to structural simulation, and I would recommend you just to join our webinar tomorrow. There's a question by Ray. In our HVAC example, if we make the room walls floor ceiling as non-adiabatic, isothermal, would it take longer to complete calculation or convergence? Ray, that's a very good question. In theory, it should not affect the duration of the calculation or the convergence. However, it has a slightly impact. And generally speaking, or as a rule of thumb, as more you restrict your simulation with boundary condition, more you simplify the physics, as faster your simulation will be computed. And Ray also said that in HVAC engineering, he's also working in HVAC engineering, and he used to use traditional old ways of calculations. And if CFD is a mainstream tool already in HVAC engineering nowadays, it's not. I would say it's not a mainstream tool so far, Ray, but that's exactly our idea. We want to make simulation mainstream tools, and we want that HVAC engineers can use thermal simulation as a standard tool. So it's basically our aim to make it mainstream and make it available for everyone. All right, and there's a question by Heather Harrison. How do I know what type of element to use for the simulations? We are basically supporting two types of elements. One are the hexahedral elements, the other are the tetrahedral elements. And while the tetrahedral elements can be used for all analyzer types, the hexahedral elements can be only used for CFD simulations. And usually we suggest to use tetrahedral elements because it gives you the better element quality, but whenever you have complex geometries, sometimes it's maybe more useful to use hexahedral elements. And if you're interested in that, you should definitely check out our documentation where we have several examples and case study explaining where you should use which kind of element. All right, it seems like I answered all the questions. Thank you very much for being here with us today, and I hope you enjoyed this webinar. As I mentioned, you will receive a link to the recording and some additional resources very soon. Yes, I hope to see you tomorrow for the last and final session of our workshop series. And yes, have a nice evening and see you tomorrow. Bye.